Day 214 of the transit. The crew member runs the routine instrument check. Pressure readings, navigation display, system status. Everything is nominal. The notation in the log reads, "Near displays harder to read than last month, adjusting distance." It does not flag as a medical event. There is no alarm threshold in the mission log software for preferred reading distance. The crew member is not wrong about the display. The display has not changed. What has changed is the shape of the eye reading it, a slow, silent deformation that began somewhere in the first weeks of transit and has been continuing at a rate too gradual to feel like a symptom, in an environment where the gravitational condition producing it does not announce itself as dangerous because it does not feel dangerous at all. Mars gravity is strong enough to make the damage feel like it isn't happening, and not strong enough to stop it. By landing day, the crew has adapted. The spare reading glasses NASA packed, called space anticipation glasses in the mission inventory, because the engineers knew they would be needed, are in use. The adaptation is complete enough that nobody files a medical incident report about their vision. The optic nerve is still swelling. The eyeball is still being pressed out of its normal geometry. The pressure accumulating behind each crew member's eyes has not resolved. It has simply been compensated for with a tool that corrects the symptom while the underlying structural damage continues on a timeline that the mission has never before tested in any human being. The mechanism begins with a fluid that most people never think about. Cerebrospinal fluid circulates continuously around the brain and spinal cord, cushioning both against mechanical shock and maintaining the chemical environment that neural tissue requires to function. On Earth, this fluid moves through a pressure system that gravity helps regulate. The weight of fluid above the head differs from the weight below it, creating a gradient that drives drainage efficiently. The eye sits at the top of that gradient. The space around the optic nerve, the bundle of tissue connecting the retina to the brain, is directly connected to the cerebrospinal fluid circulation. On Earth, at 1 standard gravity, the pressure in that space stays within a narrow range the optic nerve is built to tolerate. Remove the gravitational gradient, and the drainage system that depends on it weakens. In full microgravity, it collapses entirely. Cerebrospinal fluid shifts toward the head, accumulates behind the eyes, and the pressure in the space surrounding the optic nerve rises, not sharply, not with a headache that announces the problem, but slowly, sustained over days and weeks, at a level that the body's compensation mechanisms partially address and partially cannot. The pressure does not stop at the optic nerve sheath. It transmits forward and pressing against the rear surface of the eyeball itself. The eyeball maintains its shape through a balance of internal fluid pressure against external tissue pressure. Add persistent external pressure from behind, and the rear surface flattens. A flattened rear surface changes where the eye's lens projects its focal point. The retina shifts away from the position the lens was calibrated for at 1G. Near objects, which require the steepest focal angle, blur first. Reading distance text becomes harder before anything else does. The crew member who reaches for their glasses to read the instrument display is not losing their eyesight. They are experiencing the result of a structural change in the eye's geometry, a hyperopic shift, a push towards farsightedness that the glasses correct optically without touching the pressure that produced it. This is Spaceflight-Associated Neuro-ocular syndrome. NASA confirmed it as a documented pattern after analyzing the medical records of long-duration ISS astronauts. More than half of crew members completing missions of 6 months or longer showed measurable changes: optic disc swelling visible on imaging, posterior flattening of the eyeball confirmed by ultrasound, and in some cases, small scotomas, blind spots or gaps in the visual field that persisted after return. Best corrected visual acuity, meaning vision with the correct glasses prescription, was preserved. The astronauts were not going blind. They were becoming dependent on a corrective tool to maintain the visual function they needed to do their jobs, while the structural pressure producing the shift continued operating beneath the correction. The ISS finding that carries the most weight for Mars planning is not the vision change itself. It is the 12-month follow-up data. Scott Kelly, after his one-year mission, showed optic nerve swelling and structural eye changes that had not fully reversed a year after returning to Earth. 1 year of re-exposure to 1G was not sufficient to restore the baseline. The pressure that accumulated over 12 months in orbit left a structural residue that 1G alone could not undo in an equivalent period. A Mars mission is 3 years, 9 months of transit in microgravity, then 18 months on a surface at 38% Earth gravity, then 9 months of return transit in microgravity again, each phase adding to a cumulative pressure load on the optic nerve that no crew member has ever carried before, with no return to 1G until the journey is nearly complete. 38% gravity is the number that mission planners cite as one of Mars's advantages over the Moon and over orbital stations. It is accurate that 38% gravity reduces some of the most severe microgravity effects. Bone density loss slows, cardiovascular deconditioning is less pronounced than in full weightlessness. The crew has meaningful orientation and physical load. What 38% gravity does not provide is sufficient hydrostatic gradient to restore normal cerebrospinal fluid drainage. The threshold at which partial gravity becomes adequate for that specific purpose has not been characterized in human subjects, because no human has spent extended time in controlled fractional gravity. Mars analog data modeled from bed rest studies and parabolic flight experiments suggests the syndrome develops more slowly at 0.38 G than at 0 G, not that it stops. The crew arrives on the surface already carrying 9 months of transit phase fluid shift. The surface phase does not reset the clock. It continues it at a reduced rate. The distinction between developing more slowly and not developing is the entire medical question for a Mars surface crew. The slower rate of optic disc swelling means the crew has more time before the structural damage reaches critical levels. It does not mean the crew has unlimited time. Optic disc edema, the swelling of the nerve where it connects to the retina, when sustained at elevated pressure over a long enough period, can progress to optic nerve atrophy. Atrophy means the nerve tissue itself begins to degrade. Unlike the hyperopic shift, which is geometrical and correctable with lenses, optic nerve atrophy is not correctable with anything available on a Mars mission or on Earth once it has occurred. The glasses that compensate for the refractive change cannot compensate for a nerve that has lost fiber density. No ISS astronaut has reached that threshold. Every ISS mission ends and the crew returns to 1G before the cumulative pressure load has sustained long enough to drive the condition to that point. The data that exists comes from missions of 6 to 12 months. The Mars mission is 36 months in a gravitational environment that does not restore normal drainage. The research program has no data point at that duration and that gravity level. The first data point will be the Mars crew. The countermeasure that receives the most research attention is lower body negative pressure, a suit that applies suction to the lower half of the body, pulling blood and fluid toward the legs and reducing the cephalad shift that drives the pressure accumulation. The device works. Studies in microgravity show measurable reductions in intracranial pressure during use. The crew member wearing it experiences a partial simulation of the fluid distribution that gravity provides on Earth. The head gets a reprieve. The pressure behind the eyes temporarily drops. The optic nerve sheath pressure decreases for the duration of the session. The session lasts 2 to 4 hours. In a mission where every crew member's schedule is a resource allocation problem with no slack, 2 to 4 hours daily of non-functional time per person is a significant operational cost. The suit must be worn while stationary. It cannot be worn during EVA preparation, during active systems maintenance, during emergency response. The hours it is not being worn, the mechanism it partially offsets, continues running. A crew member who completes the lower body negative pressure protocol every day is a crew member whose optic disc edema is progressing more slowly than it would without the protocol. The words "more slowly" appear again and carry the same weight they carried before. The spare glasses in the mission inventory were packed based on models predicting the expected hyperopic shift for the transit phase and the surface phase combined. Those models were built from ISS data collected at 0G, extrapolated downward to 0.38G using assumptions that have not been validated in the relevant environment. If the shift progresses faster than the model predicted, because the Mars surface provides less drainage relief than the model assumed, the crew member may need a stronger prescription than the spare glasses provide. The glasses cannot be ground on Mars. The inventory is fixed at launch. A crew member whose hyperopic shift exceeds the available correction range is a crew member operating on instrument displays through a blur that no tool in the mission manifest can resolve. Beyond the glasses problem is the scotoma problem. Blind spots in the visual field are not correctable with optical lenses because they are not refractive. They represent regions of the retina or optic nerve that are not transmitting signal. A crew member with a scotoma in their peripheral vision does not know the scotoma is there without specific testing because the brain fills in the gap automatically, constructing a seamless visual field from surrounding input. The crew member reads the instrument display, sees what the brain constructs, and does not register that a portion of the display, possibly a warning indicator, possibly a peripheral gauge, fell in the region the nerve is no longer transmitting. The gap between what the eye is receiving and what the brain is presenting as complete visual information is not detectable by the crew member experiencing it. You are on the surface, month 19. The optic nerve swelling documented in your pre-surface baseline scan has increased from the value recorded at the end of the transit phase. The increase is within the range the research team marked as concerning, but not yet critical. Your corrected near vision is functional with the glasses you are wearing, the third prescription from the mission inventory, stronger than the second, which was stronger than the first. The mission medical protocol calls for monthly fundus imaging to monitor optic disc edema. The imaging requires 40 minutes of crew time and produces a DICOM file that is transmitted to Earth for analysis, with results returned on the next communication window, 20 minutes of radio delay each way. You are awaiting the analysis from last month's scan. Today's task schedule includes EVA suit maintenance, a procedure that requires reading component serial numbers and torque specifications from a printed reference card at 25 centimeters. You put on your glasses and begin. The pharmacological option that exists on Earth for idiopathic intracranial hypertension, acetazolamide, which reduces cerebrospinal fluid production, has been studied as a potential SANS countermeasure. It reduces the rate of fluid accumulation. It does not restore the gravitational gradient that makes drainage work. Long-term use produces side effects, metabolic changes, kidney stone risk, cognitive effects at higher doses that are manageable with monitoring and dose adjustment in a hospital setting. On a Mars surface crew, dose adjustment means communicating symptoms to Earth, waiting 20 minutes for a response from a flight surgeon who cannot examine the patient, and implementing a protocol change with no ability to escalate to a different intervention if the adjustment produces an unexpected result. The medication works as far as it goes. Where it goes is constrained by the environment it operates in. The NASA Human Research Program has ranked visual impairment and intracranial pressure among its 5 identified risks for long-duration spaceflight for over a decade. The risk ranking reflects genuine uncertainty. The condition is documented, the countermeasures are partial, and the dose-response relationship at fractional gravity over multi-year timescales is unknown. The research program cannot resolve that uncertainty without a mission that runs for the relevant duration in the relevant gravity environment. Artemis crew members on Gateway, NASA's planned lunar orbit station where crews will spend weeks to months in microgravity at lunar distance, will provide the next data increment. Gateway missions are not Mars missions in duration or gravity, but they extend the dataset beyond ISS parameters and provide follow-up data at longer post-mission intervals than the ISS medical program has tracked. The optic nerve is a structure with a fixed number of fibers at birth. Fiber loss from sustained elevated pressure is not replaced. The ISS program has operated at mission durations short enough that the crew returns to 1G before cumulative pressure produces fiber loss at detectable rates. The Mars mission duration does not offer the same margin. Whether 18 months at 0.38 G added to 9 months of transit at 0 G, added to 9 more months of return transit, produces a cumulative pressure on the optic nerve that crosses from reversible structural remodeling into irreversible fiber atrophy, is the question the mission will answer in the crew members who fly it, with the optic imaging data they transmit home every month and the post-mission scans that will be taken when they return. The human visual system is calibrated to drain fluid at 1G. Every environment below that threshold runs a deficit in the drainage system at a rate determined by how far below 1G the environment sits. Mars sits at 38% of the way toward meeting the requirement. The crew member who reaches for their glasses on day 214 of the transit is not having a vision emergency. They are at the beginning of a 36-month exposure to a gravitational deficit their visual system was never built to sustain. And the research program that will eventually characterize exactly what that exposure produces is waiting for them to come home.